Thank you all for participating in this class. It's really been a lot of fun. It's been, a great experience for me. Hopefully it's been a good experience for you participating in this class. I think the project component was exceptionally um, uh, successful. You all did very well. And I think that means that really there's nothing you have to worry about from here on out. Even if you were to participate in the final exam, it doesn't really cost you anything. It's really just extra points if you wanted to go for them, and a way also of testing your understanding and reinforcing the concepts that we've covered in this class, and an opportunity for you to end the course with this more traditional way of evaluations. I don't particularly like final exams. I don't think anybody does, but I do think they still have some pedagogical value. Even if you're a little bit stressed going into these exams, there's something about having the opportunity to review everything and try to consolidate everything in your mind that is really helpful for reinforcing the things that you've learned. So with that, we'll talk a little bit about some of the logistics of the exam. It'll be held next Wednesday in this very room, but not at our usual time. It'll be according to the course schedule. They've outlined all of the specific times. You can actually find that course schedule for final exams. You can search for it, Oklahoma State, and it'll provide the exam times based on when the class was normally scheduled during the week. Ours is Wednesday, May 8th from 10 a.m. to about noon, so roughly 2 hours. I doubt that we'll use that full time, but if you want, I'll be here that full 2 hours. You'll be allowed any and all materials that can be printed or written down. So open book, open notes, if we had a book, or notes. But anything that you want to take with you, as long as it's not a personal electronic device. So no cell phones, no computers. You can use a calculator, but I guarantee you, you will not need it. There will be almost no quantitative questions asked on this exam. It will be almost entirely qualitative questions seeking to gauge your understanding of the theory, your intuition about how certain systems will behave, and really trying to evaluate that instead of your ability to work through numerical computations by hand. So as I've mentioned previously, also the final exam is optional. If you've already done well in the course, which is true of everyone here, and you're satisfied with your grade in the class, then there's no need for you to attend, really. It's kind of at your discretion. And it doesn't count against you if you decide not to participate. But if you do choose to participate, then it'll be an extra credit opportunity. So you'll get extra credits towards the class. If you're already at an A, which is true of everybody here, then maybe it nudges you up to A+ territory if that's something that matters to you. But that's really up to you. And I won't be offended if you don't come. I'm sure I'll find a way to pass the time. So as I said, the exam will be mostly qualitative in nature, not quantitative. It'll be multiple choice is how it's going to be structured. So it's basically just a bunch of A, B, C, D, choose one of them, or where appropriate, I'll maybe ask, choose as many as apply to this question. So kind of, it'll be variable. And again, it'll focus on theory assessment of your intuition and interpretation of analysis results. It'll cover the full scope of the class. So everything we did prior to the midterm, as well as everything that came after. And a brief reminder, this is taken from our slides when we were reviewing for the midterm. We covered a lot of things in that first roughly half of the class. In terms of the theory, we went over, governing equations of mechanics for axial members, beams, and torsional shafts, as well as, we talked about boundary conditions. We talked about finite element methods, primarily in the context of one-dimensional analyses for elasticity problems. And then we did a lot of application towards solving matrix structural analysis problems for frames, trusses, beams, and just one-dimensional problems spanning a bunch of different, mostly structural engineering applications. So a lot of things that are probably more, worthwhile to review if you were to go back and, review the slides for the midterm review session. That'll be kind of a good reference. But I would still encourage you to go through, if you have the time, go through all the previous lecture slides and kind of refresh your memory on some of the theoretical topics. So I think that's going to be particularly relevant for the exam. And again, I'll provide a few examples later in today's lecture, giving you a sense of the types of questions that will appear and the types of information that you might want to review. As for everything that we've covered in the past few weeks after the midterm exam, we talked again about quite a lot of things in that sense. We talked about nonlinear analysis in a general sense, and the different types of nonlinear analysis that can show up in practice. We talked about plasticity, the theory of it, how is it implemented in a computational setting, how do we solve problems in sort of an iterative nonlinear fashion when we're solving matrix structural analysis problems that might include nonlinear material behavior or plasticity in particular. We talked about the principle of minimum potential energy and how that feeds into the development of consistent stiffness matrices in the case of geometrically nonlinear analyses for trusses, and how that general theory applies perhaps to other types of structural elements. We talked about plate theory a little bit and shells and the theory of plane stresses and plane strains, as well as plate bending under Kirchhoff-Love theory of plates. We talked about geometrically nonlinear phenomena spanning mostly a discussion of truss elements, but also we talked about how is geometrically nonlinear analysis applied to understand when will a structure buckle. So talking about elastic critical load analyses and how that gets carried out. So last thing we talked about was nonlinear solution algorithms, spanning the spectrum of Newton-Raphson types of approaches and different variations on that. So modified Newton methods, and also kind of Newton-like methods, I guess I'll call them. So that spans the spectrum of things that will be covered, everything that we've covered in this class, basically. And as for the way that things will be evaluated, it's really not at all like what we've covered in terms of how things will be assessed. We did a lot of homeworks. Those were mostly quantitative. I asked you to kind of work through either, the theory and derivations, or maybe it was like actually solving problems and giving quantitative answers. That was true also for the midterm exam. But really this final exam will be nothing like that. Unfortunately, I have this smile on my face very much like this. I had to include this. But in any case, don't worry. Obviously, there's nothing at stake here for the people present. But it's really just an opportunity to kind of test your knowledge, have fun with it. And being multiple choice means that, you have a 1 in 4 opportunity of still getting it right, potentially. So there's no reason not to guess a question. If you're not sure of the answer, you can always guess, and, you might get it anyways. All right, so with that, let's really dive into it. This is where things get a little bit more interactive. It'll be structured, I have maybe a sequence of a few sample exam problems. There'll be maybe on the order of 20 so problems on the actual exam. Depending on how quickly you work through them, it may take you, I don't know. If you go at a very quick pace, you might be able to finish in the span of like 20 minutes if you're going one question per minute, basically. But suffice it to say, I don't think you're gonna take the full 2 hours to complete the exam. But with that in mind, let's go through a few of these example problems, starting with this one. So I'll kind of pose this as a question to you all. You'll provide some kind of thinking about what you think the answer is. We'll reason through it. It'll be a good learning opportunity and a review opportunity at the same time. So which one of the following is not one of the mathematical conditions for a boundary value problem to be considered well posed? So I'm asking you, which one of these is not one of the requirements? That's, a little bit carefully phrased, but we have a few options here. Tell me, what do you remember about the different requirements for a boundary value problem to be well posed? What were there's three requirements. They're up here somewhere, but which ones were they? Stability, I hear them. You say feasibility? Uniqueness? So is that our three? What's the other one? Existence. So then we have some conflicting, we should try to reach a consensus. Why do you rationalize, uniqueness and existence versus, I guess, uniqueness and feasibility? All right. Right, right. So uniqueness, I guess, that was an issue in a few problems, right? That we considered. There were a few problems, especially when we talked about buckling analysis, where it's possible for there to be actually more than one solution to a problem, depending on how you've set it up. So that actually leads to some problems in terms of how we define a well-posed boundary value problem, right? So uniqueness is, in fact, one of the requirements. And existence, I guess, is, when is it possible for a solution not to exist? That's a good question. Yeah, it might be because of a boundary condition, basically. I think one of the prototypical examples I'll point to is if you've defined maybe conflicting boundary conditions such that, let's say, at a particular support, you say that I'm going to constrain what the displacement is at this support. But if you try to also prescribe something like the reaction force at that support, in addition to prescribing what the displacement was at that support, now you're trying to prescribe two different things that might actually conflict with one another. Ideally, if you have a support condition, you're saying, I'm constraining displacement here. It's kind of like you're saying, I don't want the support to move, so I need to impose a force here that will ensure that the structure stays in equilibrium, but without solving the problem, I don't know what that reaction force should be. So it's kind of like if you're saying, I'm constraining both displacement and imposing a boundary reaction force there, then you're kind of making it impossible to figure out what the right reaction force should be to ensure equilibrium while also ensuring that the joint doesn't move. So that can be a situation where you've basically created a problem that doesn't have a solution at all. It doesn't satisfy these boundary conditions that you've imposed. So existence and stability, we talked a lot about stability. I think that one, I don't think anybody disagrees with, but suffice it to say, feasibility, I do want to point out, I chose this terminology, feasibility, as actually, it's something that isn't particular to well-posed boundary value problems, but it is a terminology that shows up actually in constrained problems or problems that involve maybe different types of constraints. The notion of feasibility actually shows up in that context. And if you have, let's say, a contact constraint involved in your analysis, you do actually have to check whether, you're imposing a contact constraint, whether the contact forces are, strictly compressive forces. That's a condition on solution feasibility. So for a solution to be considered feasible in the context of one of these, constrained problems, maybe with a contact condition, it's really a check that, there's a physical condition or constraint imposed on the sign of the contact force always being compressive. And if it were tensile for some reason, like if the two parts wanted to move away from each other, and you assumed that they stayed in contact, but to do so, they had to maintain some kind of tensile force between them, then that solution is infeasible. It's technically not a feasible solution. So feasibility is actually an issue. It shows up in other types of problems, but it isn't necessarily related to this notion of well-posed boundary value problems. So just a little bit of extra learning because, of course, I'm going to throw that in here. All right, let's move on to the next problem. All right, which of the following solutions may result in a linear elastic finite element stiffness matrix that is not invertible? And there may be multiple of these that apply in that circumstance. So the question is, which of these different conditions may result in a non-invertible elastic stiffness matrix? And I'll provide a little bit of a hint here. I was very specific in saying a linear elastic stiffness matrix. So I'm really considering stiffness matrices that I would assemble that don't contain either material nonlinearity or geometric nonlinearity. It's just a standard stiffness matrix as we considered in the first half of the class. So when can we have a stiffness matrix that can't be inverted? In general, yeah, the mathematical condition that corresponds to is one of the eigenvalues is 0, which equivalently means that the determinant of that matrix is equal to 0. So do we have something like that here? Or with an understanding of that condition as being the reason that we can't invert a stiffness matrix, can we use that knowledge to then correlate that to maybe some of these conditions up here? You say B? So a couple different options. Let's go through them one at a time, and then I'll ask if you think it's a yes or no if it applies. So what if the structure is not constrained to prevent rigid motion? Could that mean that the stiffness matrix is not invertible? You say no? Any dissenting opinion? Yeah? You say in that case it's not invertible? Okay. And what would be the rationale for that?
Sounds like garbage.
Well, I think it's probably worth pointing out that, yeah, when you're considering like, can we uniquely solve for a problem? If you have potential for non-unique solutions showing up, maybe because the structure can still satisfy equilibrium, but it could also be translated arbitrarily or something like that. That's a situation where you could have non-unique solutions, multiple non-unique solutions. And in those situations, you can wind up with basically 0 eigenvalues in your stiffness matrix. So in those scenarios, if you have these non-unique solutions as potential solutions to your originally posed problem, that could mean, yes, you have a 0 eigenvalue, which means then stiffness matrix may not be invertible. So under that rationale, yeah, if you have some kind of rigid motion or like a poorly constrained support condition, it basically means that you run the risk of this matrix now being not invertible, which means, nominally, answer A would be one of these criteria. With that understanding in mind, what about number, B, option B? The structure is not stable due to a poorly designed configuration of the members. Doesn't this sound a little bit like a homework problem that we considered? Yeah. There was if you recall that homework problem, it presented a truss structure in a MATLAB context. You were asked to kind of run the analysis, and it gave you kind of a garbage result. It said, matrix close to singular or something like that. So that was another example where the solution to that problem to render the structure stable was to add more members or to adjust the configuration of the structure such that it became stable. It's kind of a similar circumstance still to problem or option A, where there's an internal mechanism where the structure might deform in this sort of unconstrained mode of deformation that still satisfies generally equilibrium, but this mechanism that allows the structure to deform under some kind of semi-rigid or internal mechanism that leads to this instability. So because the stiffness matrix has this 0 eigenvalue associated with that unconstrained motion, that's kind of where the non-invertibility comes about. All right, what about option C? 0 or negative material properties defined for one or more members. Well, conceptually, think of it like, what if you had a truss structure? You chose one of these elements, and then you assigned a 0 value for the Young's modulus associated with that element. How do you think that element would behave in terms of how it affects the rest of the structure? Like it's not there. Yeah, basically. You know, it's kind of funny, but some people will do this where they'll do something called element deletion, where if you want to model or kind of approximately model material failure, what they'll do is they'll actually say, okay, if I want this member to fail, they assign 0 stiffness properties to it. And it'll still be in there. It'll still be in the structure, but it basically has no effect. It's almost like you deleted the element. The more morbid terminology is called element death. But, you know, we won't go there. That's a little bit, it's too soon. Negative material stiffness, that's something that technically speaking, you could invert a stiffness matrix that had a negative material stiffness. It's really only when you have 0 stiffness that it becomes more of a problem. But negative material stiffness, even if you can invert the stiffness matrix, may not necessarily represent physical behavior. You might have negative stiffness if you have, let's say, constitutive softening behavior, where the tangent modulus of the material is going to be some negative slope, you know, as you continue to load it, you know, in some kind of like increasing load direction, maybe it's losing stiffness, so the slope should be going down. But the tangent stiffness is now negative. It's kind of a paradoxical situation where you'd like to model these things, but negative stiffness, even if you could invert the stiffness matrix, may not necessarily give you reliable results or meaningful results, in the sense that, you know, we've talked about this issue of, to be able to solve this problem of finding the state of the structure which achieves minimum potential energy, you're constantly trying to find these kind of like, you know, minimum points in the potential energy by kind of like traversing down these concave wells almost. But if you have a negative stiffness, it's kind of like you're sitting on top of a hill. So with a negative stiffness, it's kind of just going to continually drive further instability. You're going to be moving further away from the maximum points. And, you know, ideally, eventually you'll find a minimum, but it's not guaranteed, really. So C, really, maybe we can say C is true if it's a 0 stiffness that you're applying. And then what about D? What happens if you apply loads that are too large? You say it's irrelevant. And I think, you know, I'll point back to, you know, this caveat that I presented, that if we're considering really just a linear elastic stiffness matrix, then yeah, it doesn't really matter how big the loads are. The stiffness matrix will still be invertible, because we've kind of assumed in the linear elastic case that, you know, the structure's stiffness doesn't depend on the externally applied loads. That is, you know, a valid assumption up to a point. And, you know, this is basically the only one here that really, you know, you could highlight and say, you can still invert a linear elastic stiffness matrix and obtain an answer, even if you have arbitrarily large loads. But obviously, we know physically that doesn't, you know, make too much sense. If we had to, well, you know, I'll just kind of clarify, yes, it's these 3 conditions will lead to a non-invertible linear elastic stiffness. But obviously, if you were to run a geometrically nonlinear analysis, you have P delta effects, you have other things that could contribute to a possible implicit dependence of the stiffness then on the magnitude of those external loads. So yes, you're correct. You know, this shouldn't have any influence on the linear elastic stiffness, but it does on geometric stiffness. A thing to be careful about, obviously, if you're running an analysis and you run it as a linear elastic analysis, you might be missing this effect. And you have no indication that this is potentially something that you need to turn on or include and examine P delta effects. But something to keep in mind. All right, we're going, let's maybe up the pace here. All right, so let's try this. For a one-dimensional finite element analysis, which of the following solution fields will be represented as discontinuous functions? So potentially there may be a jump in the value of one of these solution fields if you were to do some kind of discretized finite element analysis. We presented a version of this, I think, in a previous lecture, but let's see if you can recall. Well, what about the displacement field? Will the displacement field potentially be discontinuous? No. And why not? Yeah, it really should be continuous. And kind of part of the reason is we've constructed the problem with that explicit consideration in mind. We've built our finite element shape functions such that they are, by design, continuous. That's a requirement for us to solve a lot of these problems, is that the solution field for the displacements must be continuous for us to satisfy basic requirements of compatibility. We can't have fractures showing up, at least not in the way that we've treated these kinds of problems in this class. But what about the remaining ones here? The strain field, the stress field, and even the internal forces in each of the members. Do these necessarily need to be continuous, or what do you think about these? You say no? Strain can be discontinuous, yeah. By extension, stresses could be discontinuous. And then assuming internal forces are computed as stress times the cross-sectional properties, then certainly all three of these last three are potentially discontinuous fields. It's important to point out, though, that this seems to conflict with our intuitive understanding that really shouldn't internal force always be this quantity that is in balance? You know, if we were to take a small chunk of material and slice it and look at the cut surfaces, you know, we'd like to say that the external forces or the internal forces acting on this kind of cut of the structure, that those are in balance, that it satisfies basic requirements of equilibrium. But in the context of finite elements, it's possible for you to actually take a cut of the structure and look at the internal forces acting across each of those cuts and find that the forces on those cuts are not actually in equilibrium. It's kind of confusing. And certainly it disagrees with our intuition that shouldn't, you know, any arbitrary cut of the structure produce some kind of subassembly that is itself in equilibrium. Yes, but also bear in mind the way that we've actually formulated these problems. We've formulated equilibrium in sort of this weak or integral average sense. So while in some cases it's possible to achieve equilibrium by considering cuts or subsections of the structure, really you can't guarantee that you're going to satisfy equilibrium on every possible cross-section through the structure. It's kind of a limitation of these finite element methods, that they satisfy equilibrium in this approximate sense. So something to keep in mind, though, because if you come across that, you might think something is going fundamentally wrong here, but it's just the nature of how finite elements are constructed. All right. Yeah, I mean, there are certain types of numerical methods that do actually try to do this more accurately. Some of them, yeah, I won't go into the details, but some of them do try to enforce equilibrium in a much more rigorous way at like a series of points at every point along a member. Some of those are called force-based elements. They introduce the force as an additional variable besides just the displacement field that also has to satisfy, you know, basic requirements of equilibrium on an almost pointwise basis. They can't do it exactly pointwise,
But I mean,
but they try.
if you got an external force,
Right. There's no guarantee even that the external forces will balance with the internal forces at that exact measured point in the structure. It's a little weird. There are simple examples that I could point to that kind of violate your basic intuition about this, but it's definitely kind of an intriguing nuance that is sometimes overlooked when it comes to finite elements. But yeah. All right. Let's do the next one. So for a one-dimensional beam element with only transverse displacement and rotational degrees of freedom at the nodes, in terms of what units are the individual entries of the beam element's stiffness matrix? So this is a little bit weirdly phrased. Let me kind of break it down. So remember, we have a beam element, right? A beam element is expressed in terms of joint displacements and rotations. And if we have this beam element stiffness matrix, let's say it's just a simple two-dimensional beam element or something like that. Or if you prefer, you can think of it as just a simple one-dimensional beam element. It should have 4 by 4 entries, right? So there's a total of 16 entries in this beam element's stiffness matrix associated with the 2 transverse nodal displacements at the ends of the beam and the 2 nodal rotations at each end of the beam. And the entries of this stiffness matrix are comprised of a bunch of numbers, but they have units. All of those entries have units. The question is, what units are those entries expressed in terms of? Are they units of force? Are they units of force per unit length? Are they force times length? Or, is it all of those? That's kind of the question. But intuitively, do you have a general intuition? What are you leaning towards? Maybe I'll provide a little bit of a hint. Imagine you had just a simple uniaxial member. Certainly, we have the relationship that we're all familiar with. If we have just axial forces, truly forces, and we want to determine what's the internal force as a function of, the element stiffness times maybe the end displacement. Certainly, displacement has units of length. The forces are kind of what we want to achieve. And so it kind of dictates what the units have to be for the stiffness. It has to then be, this units times length gives me back forces. Well, we can rationalize it should be in units of force per unit length. That's true if you have all these displacement values being expressed in terms of units of length. Things get a little bit weird when it comes to beam elements because remember, what are the units of these different displacement-like quantities? Because it's not just transverse displacement, now it's also rotation. And what are the units of rotation? Radians? Yeah. So radians, which are basically dimensionless, are yet another one of these displacement-like quantities. And so now you have this question of, well, there may be terms that involve, let's say, Ku plus maybe K theta times theta. If these are length per unit length, radians, then the units of this kind of term should then be something like, well, it just is force, right? But then there's also this other problem of not only do we want to know what are the resulting forces generated by displacements and rotations, but also we want to know what are the resulting moments generated at the end. So we might want to know m in turn, which has units of moment, which is a force times a length, right? So technically speaking, if we have then, let's say, additional terms that can show up here that depend on displacements and rotations, coming up with what are the units for these terms, then generating units of force times length, then maybe this will have to have units of force times length divided by length, let's say, or needing to generate force times length means this has to be force. For this to be, unitless times some value implies this needs to be technically force times length. Yeah, force times length divided by length, maybe squared, something like that. So technically speaking, this would be units of force then, units of force times length, force divided by length. Really, all of these things show up in the stiffness matrix. The point is, it really depends on, what are the quantities or the displacement-like quantities that show up on the right-hand side of this general expression of F equals K times U. And then what are the resulting force-like or moment units that we have to get on the left-hand side? So in practice, it ends up actually being all of these things. We have to take into account that the stiffness matrix for a beam will be expressed in terms of a bunch of different mixed units that should maybe bother you a little bit, in part because, especially if you're worried about things like numerical scaling, and if these units don't necessarily agree with one another, it may not always make sense to compare them one-to-one. If you look at what's the magnitude of this, unit of, stiffness that has totally different units than some other component in the same stiffness matrix. So the fact that not all the units match up in the stiffness matrix kind of provides a little bit of a opportunity for confusion in terms of how the units are expressed and how you compare stiffnesses. So that's something that I wanted to highlight here just through this question, which is, be careful when you compare stiffness values. Not all stiffnesses are created equal. They don't all have the same units. So you have to be a little bit careful in how you're making those comparisons, especially when you're dealing with beams where you have, displacement degrees of freedom and rotation degrees of freedom. Those two things have different units in the same way that the forces and the moments, they have different units. So just be aware of that. Be careful. Yeah. All right.
If you only have transverse displacement, you still have the force per unit.
Let's see. If you only have transverse displacement degrees of freedom, let's say, if you can express everything in terms of displacement degrees of freedom only, then you could probably proceed in coming up with some kind of resulting conjugate forces associated with those displacement only degrees of freedom that are truly expressed in terms of forces or units of force. And the stiffness quantities would also then be all force per unit length. So if it was really, strictly only transverse displacements and the only kind of forces you cared about were the transverse shear forces, then yes, I think you would be able to reduce everything down to just force per unit length. In general, though, with these general beam elements, it's got to have that mixture. It's going to include both of those, or all three of these in this case. Yeah.
But don't we not have the axial?
Well, in the axial case, you'll have, force per unit length for, the simple case where it's just forces expressed in terms of just axial displacements. So, whether it's an axial force or if it's a shear force, whether it's an axial displacement or a transverse displacement, those units are all kind of comparable. It's really only when you get into, moments instead of forces or rotations instead of displacements that you kind of have to consider these different unit systems. Yeah. All right. Number 5, let's see. At a minimum, how many displacement or rotation boundary conditions are required to sufficiently constrain a 3-dimensional truss or frame structure such that it doesn't move rigidly? I think this probably makes sense in the context of 2 dimensions. If you're considering a 2-dimensional structure, maybe that's a good place to start. How many support conditions do you need to define to prevent this 2-dimensional structure from translating or rotating? Three? Yeah, I would agree. There's, fundamentally, you're constraining against 3 types of rigid motions that can occur. There's translation in the X or the Y, and then there's rotation in the plane of whatever this 2-dimensional kind of setup is. In the case of 3 dimensions, extending that kind of intuition, what would be the case? How many different rigid modes of deformation are possible in a 3-dimensional setting? You say 9? Thinking in terms of maybe 3 by 3? Any other ideas? We already said 2 is probably, 2 would be sufficient, or rather, 3 rather constraints is sufficient for 2 dimensions. So it's got to be one of these. How many say it's 6? You say 6? How many say 9? Several say 9. Okay, well, I don't know if maybe I'm like dating myself here, but does anybody remember, like maybe it was either PlayStation or one of these like controllers for one of these older gaming systems had a controller that was the so-called 6DoF controller that was intended to measure all different types of like rigid motion, and you could like shake the controller and it would control all these different modes of rigid motion. I forget exactly what the company was. But in any case, I don't want to serve as an advertisement. But the idea is actually it is 6. It has to do with quantifying 3 modes of rigid motion, so translation in particular, and then 3 modes of rigid rotation. It's kind of like if you were to look at a single node in a 3-dimensional structure. A single node in a 3-dimensional structure has potentially 6 total degrees of freedom, 3 translations and 3 rotations about each of the 3 axes. And certainly you would all agree if you had a 3-dimensional structure that was just a cantilever beam and you fixed one of the ends of the cantilever beam, that would constitute a stable structure that's sufficiently constrained against all types of rigid motion. And it's constrained by basically taking one of those nodes and fixing all 6 of its degrees of freedom. So that's one way that you can simply think about it. But you can also think about it in terms of just 3 translations you have to constrain and 3 rotations. So 6 total degrees of freedom. All right. Now getting into the second half of the class, well, we might not have time for this, so we might have to close it out here. I'll still upload these slides if you want to take a chance to kind of review some of these extra questions after the fact. Some of them are particularly interesting, I think. But, test your knowledge. If you have questions, feel free to come to me. At this point, does anybody have any questions either related to the exam or related to some of these questions? Yeah. All right. Well, with that, I'd like to thank you all for your attention and for your participation in this class. Well done, everybody. Well done.